Buffer solutions and the control of pH. Buffer solutions work based on the common ion effect, where adding more of an ion that is already present in a saturated solution causes a shift in the equilibrium via Le Chatelier's principle. A properly prepared buffer solution will resist the change in pH even when an acid or a base is added. Here's an example of a common ion effect problem. This illustrates the common ion effect. So we want to know what the magnesium ion concentration is in a solution when you add sodium hydroxide to a saturated magnesium hydroxide solution until the concentration of hydroxide is 0.010 molar. To solve this, we'll need to write a solubility equilibrium and make an ice table. Here's our solubility equilibrium. Solid magnesium hydroxide in equilibrium with magnesium ions and 2 moles of hydroxide ions. Our KSP expression is just the concentration of magnesium ion times the concentration of hydroxide ion. But we're given the concentration of hydroxide ion. We can substitute that in. Concentration of Mg2 plus times 0.010 equals KSP, 5.6 times 10 to the negative 12th. So if we want to solve for the magnesium ion concentration, we'll divide both sides by the hydroxide concentration. KSP equals, or rather, KSP over concentration of hydroxide squared equals the concentration of Mg2 plus. So that's going to be 5.6 times 10 to the negative 12 divided by 0.010 squared. So punching that into the calculator, we get 5.6 times 10 to the negative 8th. And of course, that's in units of molarity. So adding sodium hydroxide decreased the amount of magnesium in solution. So without adding the NaOH, we'd use X for the concentration of Mg2 plus in our KSP equation, and we'd use 2X for the concentration of OH minus in our equation, and then we'd square it, which would give us 4x cubed equals 5.6 times 10 to the negative 12th. So x would be the cube root of 5.6 times 10 to the negative 12th divided by 4. Which would give us 1.1 times 10 to the negative 4th molar, right? So, again, this is common ion effect. It reduces the solubility. Buffer solutions make use of the common ion effect. Every buffer solution has 2 components, one of which is a weak acid. So, the generic formula for a weak acid is HA. And here's the equation for the ionization of the weak acid. So, each acid molecule can split up into an H plus ion or a hydronium and an A minus ion. Now, A minus is the conjugate base. And we need a way for the buffer solution to introduce more A minus into the solution. And the way we do that is by adding a salt of the conjugate base, like NaA or Ka. This guarantees that it will be soluble if you use sodium or potassium as the ion. So an example might be HNO2, which is nitrous acid, and KNO2, a soluble salt of the nitrite ion, the conjugate base. So here's the equilibrium. HNO2 splits into H plus and NO2 minus, and the potassium nitrate splits up into potassium and NO2 minus. So on the right hand side we've got H plus 2 NO2 minus. One of these comes from the acid and one comes from the salt. And then we've got K plus, which is a spectator ion. Now, let's say we add acid to the solution. It can react with stuff on either side, but what's going to happen is H plus will react with NO2 minus to make more HNO2. So, in other words, the concentration of the hydrogen ion is essentially unchanged, and there's no change in pH when you add an acid. Now let's say we add a base. That means we increase the concentration of hydroxide in solution. So any OH minus added will react with unionized acid, HNO2, to give us H2O, a liquid, and NO2 minus. Again, the change in H plus concentration is effectively zero. So whether you add an acid or a base to your buffer solution, the pH is unchanged. Your blood uses the carbonic acid hydrogen carbonate buffer system, and the Ka of carbonic acid is 4.4 times 10 to the negative 7th. The pH of a buffer solution is equal to the pKa plus the logarithm of the concentration of the base over the concentration of the acid. Now, blood is buffered at a pH of 7.4. Normal blood has a carbonic acid concentration of 0.029 molar. What's the concentration of the hydrogen carbonate ion in normal blood? This equation, by the way, is called the Arrhenius equation. So when we're trying to find the concentration of hydrogen carbonate, that means we're trying to find the concentration of the base. So the first thing we're going to do is subtract the pKa from both sides. That gives us pH minus pKa equals the logarithm of the concentration of the base over the concentration of the acid. Now we're going to have to take the inverse log of both sides. In other words, 10 to the. So 10 to the power pH minus pKa equals concentration of base over concentration of acid. Multiplying both sides of this equation by the concentration of acid, we end up with the concentration of base equals the concentration of acid times 10 to the power pH minus pKa. So, just to refresh your memory, the Ka value is 4.4 times 10 to the negative 7, so the pKa is the negative log of that. Negative log of 4.4 e negative 7 gives us a pKa of 6.36. And so here's our concentration of acid. And we want the concentration of the bicarbonate ion, HCO3-, so that's going to equal 0.029 molar times 10 to the 7.4 minus 6.36. Which gives us 0.317 molar. Here's a quick exercise to try. Which of the following would make a buffer when mixed together? And so we have some choices. Remember, we need a weak acid and its conjugate base. HCl wouldn't work because it's strong. Same with HNO3, H2SO4, and H2SO4. However, HNO2, that's a weak acid, and NaNO2. That works. So only choice D would work. None of the others would work.